Hello again, students. Back here for lesson number 2 of Inference for Regression. Brought to you again from my basement in sweatpants and shirt and tie, making sure to keep the business element in play. Looking at what gaming system is going to come up after this lesson, and still awaiting anybody who wants to play any online matchups. Thanks a lot, Max Lauerman, for being the one person to offer up a matchup. Again, minor problem is I don't know how to get these online matchups. Again, I'm 37 years old. I'm not like you all. But hopefully we get a chance to have some fun along the way here, and obviously when we get to interact over whatever other mediums here between Google Hangouts and Schoology conferences and stuff, we can have some fun, discuss this stuff a little more. But if you follow along here for the second and final inference for regression video that has to do with confidence intervals and significance tests, our final confidence interval and significance test lesson of the year. And what happens in the regression world is we come largely around this idea of if the slope is 0 or not 0, statistically speaking. And clearly, when you look at this gas consumption versus year scatter plot, there's 10 points on it and a line that clearly has a positive slope. But again, these measurements, there's certain levels of variability, and these obviously fit pretty close to the line, so it doesn't look like we're going to have much variation in the slope. But if there were some more points like this around here, would there be enough evidence that with the errors and the standard error of the slope that I was talking about last time, would it be possible that that this actually just returned a very positive slope, but maybe the slope is actually more like this when we look at the rest of the sample, okay? Because that would mean there's some other points up here or something like that. But so what we're really testing is the idea, and it's not always 0, but most of the time it ends up being something like this, where this is greater than, less than, or not equal to 0. There's actually one that, if we get to your unit test, there's one on your unit test here that's not 0. It's a different number, and it tells you what to put in there. But this, again, that beta is the population slope. If you recall, B goes to beta. So it's asking, is the population slope 0, or is it something other than 0? Is it positive? Is it negative? Is it just something that's not 0? And clearly here the sample shows positive, but again, the sample, there's variability in that, right? And so we don't know for sure if we had 10 dots here, if we were to have a whole population of dots, would we have, or were we to take another sample from these 10 years, would that sample return that same positive slope, or would it be something different? So looking here at the steps for the inference procedure first, I noted before the hypotheses here, again, almost always 0, can be something other than 0. But that's typically what you'll see, and you'll just have to look for the question, is there evidence? And what we call here is we talk about, is there a true linear relationship between the variables? And what we mean by true linear relationship is basically as our x's go up, do our y's change? And again, that could be up or down. Do our y's, are we going like this, or are we going like this? Or is it something where it's believable that this is truly horizontal, and as the x's go up, the y's aren't changing at all? Okay, and the slope could be 0. So that's really what we're looking at. And what we mean by, if you go back to the height and weight, as height increases, do we have statistically significant evidence to show that weight also increases? Or are the samples do they vary so much that it's plausible to say that as your height increases, your weight doesn't increase, which, if they're fully grown folks, could be the case. But it's, in this case, most likely something we'd reject in favor of a positive slope there. Well, true linear relationship just means, do the y's change with the x? Okay, do the y's change with the x? Now, in order to run this, we have 5 conditions here. And these 5 conditions, you will never have to really fully verify them, but there might be a question, like a multiple choice question, even on your progress checks here, that will kind of ask how we verify it. And I'll just go quickly through them. First of all, to remember all 5 of them, there's an acronym, LINER, and it starts with linear. And linear just means, is the original relationship linear? So is the original scatter plot something that the points are in a straight line and there's not some curve in that line? Independent just means that each dot in the scatter plot is independent of the other ones. In other words, there wasn't one person, or if it's whatever it is, and whatever each dot represents, if it's a person, is that person not influencing another person or another dot, if you will. Normal goes back to what we talked about in the last lesson, which is the idea that we have normal residual values at every spot on our line. And that just means, again, that for any given x, the y values are normal. Equal variance means that the residuals are about the same, so that means that s is constant. Okay, so that's s constant. And what you'll see there is, like on a residual plot, is the scale pretty consistent all the way throughout. An issue for equal variance would be if you had a residual plot and these first points were really close, and then all of a sudden they went all over the place as we got deeper into the further along the x. That would be an issue with equal variance. Equal variance should be that these are all kind of spread out the same amount. And finally, random is that it's a random sample, which obviously we usually see as number 1. It's number 5 here, partially just to make this little acronym work. The actual calculations themselves are pretty nice here. The test statistic is slope over standard error of the slope. Again, those two values you will typically get right off of your computer printout. Sometimes the computer printout will not give you the t, and so you just have to take the b and SE of b, which will be given to you, and just do that division. The only thing that could change with this is minus 0, okay, which is the null hypothesis value. If the null is not 0, then you do have to subtract something else. So you may see a spot where the null is 1.5, and so it's asking if the slope is any different than 1.5, so you would subtract 1.5 right there. Degrees of freedom is n minus 2 this unit, and that's because there's two variables. There's an x and there's a y. And so there's a degree of freedom for each of those. And then the p-value, the computer printout does give you the two-sided p-value in a lot of them. And so it's already giving you that. But you can also use your TCDF, which again is second vars on your calculator. Okay, and you can use that to get to your TCDF. And again, lower bound, upper bound, degrees of freedom. If it is a two-sided alternative, make sure you multiply that TCDF by 2. And again, what you're thinking about with the TCDF is if our test statistic is here and it's going this way, then that's negative 99 to our, what would be a negative t. If it's here and it's going this way, that would be t to 99. And then again, multiply by 2 if it's two-sided. Conclusion is very much the same. You can see here the first part is, is p less than or not less than 0.05. We reject if it is less than, we fail to reject if it's not. And if we do reject, that means there is evidence of a true linear relationship between height and weight, again, which means the slope is something other than the hypothesis, which is typically 0, which could be positive or negative. If you fail to reject, that means we're basically saying that the slope could be 0. Okay, and so that's what failing to reject here means, and that would mean there's not evidence of a true linear relationship. So again, the whole reason we're doing all of this is to see if we can show, statistically speaking, that the slope is not 0. Here's an example of that. Okay, so in this, back to this quiz average and final, if we start with beta equals 0, beta does not equal, actually, let's just say positive here, so let's go greater than 0. We talked about what beta stands for, and beta here would be the true population slope. And again, beta, the reason it's population is beta represents population, B is the sample. So true population slope between quiz average and final. Okay, so that's what we're going to test here. We have our conditions, which we're just going to roll past. Same thing, conditions-wise. The test statistic, again, B here is 0.7513. 0.7513, oops, sorry. Okay, over SE of B, which is 0.1414, and that equals, and you can see this one actually gives you the test statistic there, is 5.31. the degrees of freedom here. Okay, it doesn't, sorry, I covered it up there, but there's, in this case, there would be 48 degrees of freedom. And there were 50 total points to begin with, so it'd be 50 minus 2 equals 48. They'll be clearer on that with degrees of freedom, so don't worry about trying to get to know that part. And then the p-value. Okay, and the p-value here, they give us a p-value. Again, that is the two-sided p-value, and we only went with one-sided here. So technically it's 0.000, actually divided by 2, because we got to go back to one-sided, right? If it's giving us the two-sided and we only used one-sided, then we, instead of multiplying by 2, we've got to divide by 2. And we don't really have any other information to say anything else, so it's still 0.000. Okay, so we've got the big three: test statistic, degrees of freedom, p-value, and again, our p being 0.000 is less than 0.05, so we reject the null hypothesis. And again, I'm just giving you a brief version here. So there is statistically significant evidence of a true linear relationship between quiz average and final. Okay, so this again would be the question: is there evidence of a relationship between quiz average and final? And what we found here is that we have evidence of a positive relationship. In other words, we could get a bunch more quiz averages and a bunch more final exams. The slope is not getting back down to 0. We can see the slope was 0.75. It only varied by 0.14 with that standard error of the slope, so it wasn't, you can see we had to go down over 5 of those to bring that slope down to 0. Again, judging by the test statistic, if you take this number times 5.31, that will give you that, which is how much it's above a slope of 0 based on the standard error. Don't worry about that. If that seemed to go over your head, that's okay. And then lastly here, confidence interval side. So at the confidence interval, again, we're trying to estimate the true population slope between, in this case, it would have been quiz average and final. It's the exact same conditions, okay? The degrees of freedom are still n minus 2. The only new thing here is we get the B and the SE of B again, but you got to get the T star from your chart, okay? And so you'll get a confidence level and your degrees of freedom, and you'll go to the chart again, that T chart, and you'll go to the confidence level that's on the back page, find that, and just scroll up to that degrees of freedom, and we can talk about that live if we want to. And then in the end, we are, typically 95% confident that our interval from such and such to such and such contains the true population slope between quiz average and final. Okay? And so lastly, the steps for the confidence interval. One, the optional step is that we are going to estimate the population slope between quiz average and final exam. Okay, and from there, we have our conditions again right out of the gate. And from the conditions, then we are going to go to our degrees of freedom, which in this case, our degrees of freedom are 50 minus 2, or 48 degrees of freedom again. Let me just bring up the T star value as well. So the confidence interval, again, is B plus or minus T star times SE of B. Now, this value here, the B, again, is 0.7513. Okay. When we go to our tables and charts, you'll actually see that there's not 48 degrees of freedom. So what we do is we go to the next value lower than it. You can't go up again. That's suggesting more accuracy than we have. So if I go to 95%, and I'm going to actually go to 40 degrees of freedom. So I'm going to take 40 degrees of freedom on the chart, and I'll just note that here. And at 40 degrees of freedom, the T star is 2.021. And then my SE of B is 0.1414. Okay, so I get my margin of error there, I subtract it, and then I add it, and you can see it's going to be about 0.30 is my margin of error. If I take the 2.02 times 0.1414, just under 0.30, so our slope is somewhere from 45 to 1.05 roughly. I'm not going to calculate it on here, but something about 0.45 to 1.05. And that just again means that as our quiz average goes up by 1, that our predicted final is going to go up by somewhere in this range on average. Of course, the big thing for us is that 0 is not in this interval. So we know that the slope is going to be positive. And it's not just that this one sample produced a positive slope. We're going to get a positive slope essentially every time because we're clearly in a positive slope area here with this confidence interval. So in the end, we are 95% confident that our interval, and again, I used 0.45 to 1.05. It's not exactly that, but I use that. Our interval contains the true population slope between quiz average and final. And that is the confidence interval. So you can see test and interval all about slope. Usually it's about 0 slope versus not 0 slope. Sometimes it does vary from that, but hope that this gives you enough background to get started. And like I've said previously, would love to take questions on this live after you've had a chance to look at the progress checks and the assignments, and so you can figure out where your questions may be. Thank you all, and we'll talk to you soon. Bye-bye.